Welcome to the presentation of our paper, Global Path Integration and Attentive Graph Networks for Multi-Agent Collision Avoidance. In this work, we address the challenge of non-communication multi-robotic collision avoidance in complex and dynamic environments. Global planners play a crucial role in multi-robotic systems by predicting efficient paths and guiding the robots towards their goals. Without a global planner, robots may become stuck in local minimaps, failing to navigate through complex environments efficiently. While many navigation methods are trained using a single goal point, they rely on a running waypoint from a global planner to avoid getting trapped in such local minimaps. However, simply introducing a running goal point along the global planner's path isn't a complete solution. Traditional methods tend to over-focus on these temporary waypoints as they have been trained to treat them as their final goal. This overemphasis can introduce new local minima, where the robots become fixated on intermediate targets rather than maintaining a broader perspective on the overall path. Our approach addresses these issues by separating the goal point from the global path in the observation space, letting the network learn when to focus each objective. Secondly, our network leverages both raw sensor data for understanding complex environments and the process data for tracking dynamic objects. By incorporating attentive graph neural networks, we allow the model to handle a seamless number of neighboring agents, where the attentive mechanism learns to focus on the most relevant information in the neighborhood. Now, let's dive into the results, where we evaluate our approach across various challenging environments. These scenarios were carefully chosen to test the robustness and adaptability of our model. The random environment is designed to simulate highly dynamic and unpredictable scenarios with randomly placed obstacles and agents' positions. Our model excels in this environment, demonstrating a high success rate and low collision rate, hereby highlighting its adaptability in ever-changing configurations. In the circle environment, agents start along the circumsphere of a circle with their goals directly opposite. This setup tests both individual navigation and cooperation behavior as agents converge towards their goals. Models that overfixate on temporary waypoints often struggle here, leading to collisions in the center as agents are crossing paths. However, our model avoids this pitfall by effectively balancing the global path with the final goal. The doorway environment emphasizes coordination, where multiple agents must pass through a narrow passage. Our model is not the fastest to handle this bottleneck. However, it achieves a higher success rate compared to the other baselines, and with zero collisions. Finally, the hallway environment requires agents to swap positions within a confined space, testing both navigation efficiency and coordination. Our model's ability to navigate and avoid collisions in this scenario further demonstrates its robustness in complex and crowded environments.